Good afternoon to all of you. Today in this class, we are going to discuss about an important topic in steel design. We all know steel design is an important topic in civil engineering itself. So, what is the advantage of steel? Just think about that small things. We all know steel is a universally accepted construction material. It is mainly due to two important factors. One is its strength to weight ratio, which is very high compared to that of concrete or other material. And another important factor is that it has a resale value. At the end of this life cycle, if we demolish this structure, in the case of concrete, we can use this mainly for landfilling or some kind of dumping. But steel has a resale value. It is highly important. That's why, mainly due to these two factors, steel as a construction material is getting more and more importance nowadays. So, design of steel structures is definitely an important topic. In that, today we are going to discuss about design of beams. Design of steel beams. Actually, the correct word we have to use is flexural members. But generally we can say a beam. Beam is a flexural member. Apart from this beam, slab is another example for flexural member. Steel is mainly used for column, beam, truss, tension member, for all those things, not for slab. That's why I am telling it as beam itself. Now, there are mainly two types of beams from structural point of view. From shape, we can say rectangular beam, I section, hollow section, pipe, anything which can be fabricated using steel elements, any shape. Now, our main aim is to analyze or understand what is the structural behavior of beam. That's why the classification of structural classification is of prime importance. There are mainly two types of beams from structural point of view. First one is laterally supported beam. So definitely the next option is laterally unsupported beam. Laterally unsupported beam. This is the main important classification. Now, what is meant by this lateral support? From a competitive exam point of view, usually this idea is an important factor, because in many occasions some small questions related to this lateral support and laterally supported beam and unsupported beam is asked. Now, consider an I section. If the beam is a sagging member, then the top flange is compression member, compression flange, and the bottom one is tension. In between there is a web. Why I am selecting I section, not channel or any other shapes, angles? Most commonly used beam element is I section. That's why in steel table or SP6 itself, the name or specification for I sections is something like ISMB or ISHB or ISLB. The last letter is B. It indicates that it is mainly used for beam. So I section is the most commonly used section for beams. Now this is the top portion is compression flange. The externally applied load directly coming to this compression flange. Now the breadth of this compression flange, usually it is denoted as BF, and say it is having a thickness TF. This BF divided by TF ratio, width to thickness ratio, is comparatively less. That means the element is a thin member, so it has a tendency to buckle. Once it is buckled, its load carrying capacity gets reduced. The buckling may be in any direction, that is the exact word we have to use. For example, the simplest condition or simplest case is that this section may buckle like this. I am exaggerating this buckling in order to understand. This much of buckling is practically not possible, but in order to understand the concept, I am exaggerating the drawing. See, this is buckling. It is one possible option. Apart from this, it can buckle on the other way. The web is like this, and the compression flange is twisting. That phenomenon is termed as lateral torsional buckling. The main difference between laterally supported beam and laterally unsupported beam is this one: lateral torsional buckling. Lateral torsional buckling. Due to this lateral torsional buckling, the strength capacity, the moment capacity or load carrying capacity of the beam is reduced considerably. In many cases, if we compare a laterally supported beam and an laterally unsupported beam of same cross section, say ISMB 350, once if it is used as a laterally supported beam, say its moment capacity is MP, plastic moment, that's why I am writing it as MP, or due to the notation which we are using in IS 800, let it be MD. That is for laterally supported case. For laterally unsupported case, let the moment capacity be MD dash. Definitely MD will be higher than MD dash. Many cases, this difference or MD dash is of range 50 to 60% of MD. That is, there is a reduction of 40% moment capacity. It is due to the lateral torsional buckling. Now you may got some idea about what is the difference between laterally supported beam and laterally unsupported beam. Now how this lateral support is provided, that is the next case. If from this we can understand that always provide lateral support, that is the best option. In order to get the maximum capacity of the given cross section, it is better to provide lateral support. How we can support the compression flange laterally? One case is, encase this compression flange in, say there is a concrete slab which is placed over this steel beam. Encase this compression flange inside concrete. then it cannot move or buckle in any other direction. It is laterally supported. And another option is, say this is compression flange. There is a concrete slab which is placed above this. Then provide some connectors in between in order to support this element. These connectors are called as shear strut, or generally we can say shear connection. By providing shear connections, we can laterally support the beam. Thus, we can achieve the condition of laterally supported beam. Now, that is the main difference between laterally supported beam and laterally unsupported beam. Now, what is the design considerations of a steel beam, or what are the failure modes, possible failure modes of a design of a steel beam? Once we understand these failure modes, we can easily design a section. As per IS 800, there are mainly 5 failure modes for a beam. First one is obviously moment capacity or bending moment. And the second one is shear or moment failure or bending failure. Then shear failure. Third one, deflection. As steel is a ductile material, it is having high deflection compared to that of concrete. So, the actual deflection will be within the permissible limit. That is the deflection criteria. Fourth one, web buckling. And last one is web crippling. These are the 5 failure modes of a steel beam. Let us discuss all these points one by one and understand what is the main theories or ideas behind these things. First one, moment or bending failure. The basic idea is that the moment due to external load, which can be live load, dead load, wind, snow, whatever it may be. The moment due to all the external load, let it be M, should be or must be less than the design capacity of the given section. If this condition is satisfied, the given section is safe under bending. We can easily calculate what is the design moment depending upon the boundary condition, span, nature of beam. For simply supported beam, we all know what is the bending moment. The maximum bending moment is WL square by 2. WL square by 8. The maximum shear force is WL by 2. So, the maximum bending moment which is coming to this beam should be less than the moment carrying capacity of the given section. Now, how we will calculate this one? That is the moment capacity MD. The formula given in IS 800 is MD is equal to beta B set P Fy divided by gamma M naught. That is the first formula given in IS 800. Now, what is beta B? What is set P, Fy, gamma M naught? Beta B is a constant which depends upon the nature or type of the section. I will explain this. Then set P is plastic section modulus. And Fy is yield stress. Gamma M naught is the factor of safety. Now, if you look to this formula, if you remember the basic idea of design of a flexural member is in any case, whether it is steel, concrete or timber, whatever it may be, it is based upon simple bending theory. According to this simple bending theory, the equation is F is equal to M by Z, or M is equal to F into Z, or precisely FB into Z, where FB is the allowable bending stress, Z is the section modulus of the given section. This equation is obtained by that simple bending theory equation. M by I is equal to I will write it a little bit later. Okay, so this is the basic idea. M equal to bending stress F into Z. See, compare these two equations. There is one term F, here is also one term F. Z, section modulus, here is its or section modulus itself. Now there is another term beta B and one term gamma M naught. The allowable bending stress can be represented or can be taken as Fy divided by gamma M naught. Now section modulus is plastic section modulus. Beta B is a constant which depends upon the nature of the section. How we will calculate the value of beta B? If you go through IS 800, there is just below this equation, the beta B value is also given. Beta B is 1 for plastic and compact sections. For semi-compact section, the beta B value is ZE divided by ZP. That is the equation given in IS 800. Now, what is plastic section, compact section, semi-compact section? What is these things? Actually, this represents the ability of that section to carry a plastic moment, or the ability of a section to generate plastic mechanism. We know there are two types of analysis. One is elastic analysis and the other one is plastic analysis. The former design considerations, that is IS 800 1984, was based upon elastic analysis method, which is termed as working stress method. Now we are following the second option, that is limit state design, which is based upon plastic analysis. The plastic moment capacity of a section is very high compared to that of elastic moment. For rectangular section, that ratio is 1.5. MP divided by ME. Plastic moment divided by elastic moment is 1.5. 50% more. Or in other way, we can say ZP divided by ZE. That is called as shape factor. Okay, let it be there. Now, plastic sections, compact sections and semi-compact sections, there is another option or another classification which is called as slender sections. It is always advised to avoid slender sections. The best one is plastic, next is compact, then semi-compact. The most avoidable case is slender sections. Now, plastic sections are capable of developing plastic moment, and beyond this plastic moment, they can do something more. At the same time, compact sections, their capacity is up to MP only. Then, for semi-compact, it is slightly lesser than MP, in between ME and MP, we can say. That is the nature of these sections, the structural behavior of plastic, compact and semi-compact. Now, how we can understand whether the given section is plastic, compact or semi-compact or slender? For this, in IS 800, there is a table which is table 2. In table 2, depending upon two factors, first one is B divided by TF and the other one is D divided by TW. The first term is related to flange, that's why TF. The second term is related to web, that's why the other term W. Depending upon the value of this ratio, we can easily find from the table itself, we can easily find what is the nature of this section, whether the given section is plastic, compact, semi-compact or whatever it may be. There are some values given in table 2. Those values can be asked for some competitive exams like GATE. For example, for plastic sections, the B by TF value. What is the permissible value for B by TF? Similarly, what is the permissible value for D by TW? Those things can be easily understood and you can easily remember. Now, similarly for compact, that value is 10.5. This B by TF value, and D by TW value is 105. Similarly, there are other values also. Once you refer the table 2, which is given in table page number 18 of IS 800, you can find the value of B by TF and D by TW. Then after looking to that table, you can find whether the section is compact, semi-compact or plastic. Once the nature is known, beta B value is obtained. Plastic section modulus is a sectional property. Fy is the yield stress. Gamma m naught is the factor of safety. The factor of safety value is, in most cases, it is 1.1. Here you can understand, or you have to remember one important term, that is, in IS 800 there are mainly two stress terms, Fu and Fy. One is Fu is ultimate stress and Fy is yield stress. The factor of safety accompanying Fu is gamma m1 and this is gamma m naught. Always, in any case, if you use the term Fu, the accompanying gamma term is gamma m1 and that value is 1.25. For gamma m naught, that value is 1.1. This is in most cases. There are some special cases where this value may change. So here also you can see the term is yield stress Fy. So the factor of safety term is gamma m naught. This is a basic equation for calculating the moment capacity. For this, there is another clause in IS 800. In order to use this equation, the design shear force, let it be Vd, then 60%, 0.6 Vd should be greater than the shear which is due to the external load. If this condition is satisfied, then those section is referred under low shear condition. The 60.6 Vd is greater than shear force due to external load. Then you can use this equation. Otherwise, you have to use another equation where the ratio between this V and Vd and another term which is MFD, then another equation is given in IS 800. which includes the effect of high shear. If 0.6 VD, this condition is not satisfied, that is 0.6 VD is less than V, those beams are considered under high shear condition. You cannot use this equation. There is another equation for calculating the moment capacity of those sections. Now, here is a term VD. How we will calculate the value of shear capacity, which is VD, which is in term which directly moves us to the next section, that is the next failure mode, that is shear failure. Next failure mode is shear failure. Simply, the applied shear force should be less than the shear capacity. Basic logic. Now, how you will calculate the shear capacity VD? According to our code, the shear capacity can be written as FYW into AV divided by root 3 into gamma m naught. FYW is the yield stress of web. AV is the area of web. Gamma m naught is, as I said earlier, always the accompanying, if the stress term is yield, the accompanying term will be gamma m naught. And it is shear, that's why another term root 3. That is a idea writing behind this equation. Now, what is AV? This is shear area or area of web. In I sections, the general assumption is that the moment is mainly carried by flange and shear is carried by web. So, the shear area will be definitely web area. That's why AW. For rolled steel sections, as I said, ISMB 300 and all those things which are given in SP6, the AW area, that is shear area, is H into TW, where H is the overall depth of section, TW is the thickness of web. For fabricated sections, we have to use D into TW, where D is the depth of web only. The difference between H and D is that H is the overall depth, which includes that top and bottom flange thicknesses also. But if we consider the web thickness only, excluding the flange, that term is D. That is the area of shear. So the basic idea is that the shear capacity of given section should be greater than the applied shear or shear force due to external loads. In some question papers, this permissible value is often asked. What is the permissible value for shear in steel beams? You can easily say it is FYW divided by root 3 and gamma m naught. Obviously, gamma m naught will be there. Remember, anytime if you are writing shear, there will be a root 3 on denominator. Shear is always with root 3 and Fy is always accompanied by gamma m1. This is one important factor because it can we can expect some questions like this. It is asked, that's why I am telling this. Actually, it is very simple. What is a term related with, what is a factor of safety term related to yield? It is gamma m naught. Fu, it is gamma m1. Okay. Now let us move to next condition, that is deflection criteria. The actual deflection, say delta, should be less than the allowable value. Allowable value depends upon the type of beam, the type of structure which it is supporting. For simply supported beam, the value may be L by 300. For cantilever, that value will be less than this. Okay. Similarly, for a continuous beam, the allowable deflection will be still higher. So, that allowable deflection value depends upon the boundary condition, the type of beam, and the structure which is supported by this. If this beam supports an element which is having allowable deflection of very small, then the allowable deflection of beam also must be less. Okay, like that. So this actual deflection must be less than the allowable value. For simply supported beam, that is the easiest case, with a uniformly distributed load, the allowable deflection or actual deflection is 5 by 384 WL raised to 4 divided by EI. Here you have to understand, or you have to remember one thing. This term W, this is not ultimate, this is service load only, not ultimate load. What is the difference between ultimate load and service load? Service load multiplied with 1.5, that is a load factor, which is giving the factored load, ultimate load, factored load or ultimate load. When we are calculating bending moment, shear force, all those things, we have to use factored load. For deflection, we have to use service load. What is the reason? Because deflection, check for deflection or deflection criteria is limit state of serviceability. All other things are limit state of collapse. This is limit state of serviceability. That's why we are using service load. Okay. That is about deflection. Now, last two terms, that is web buckling and web crippling. Now, web buckling. As I said earlier, and consider an I section which is having two flanges, one at top and one at bottom. The top flange, let it be compression flange, and the bottom flange tension. In between there is a web. The depth of web is usually very high compared to its thickness. Now, due to this huge depth to thickness ratio, it is a slender element, so it has a tendency to buckle. Slender members has a tendency to buckle due to the application of external concentrated load or support reaction. That this is support reaction condition. External concentrated load. Due to this external concentrated load and support reaction, the thin web portion may buckle out. Actually, here this web portion is acting as a column. That is a structural behavior. So, the load carrying capacity FW, let it be FW. The compression load carrying capacity of web should be greater than the applied external load or support reaction. If this condition is satisfied, we can say the section is safe under web buckling. Now, how we will calculate this one? For this, as I said earlier, it is behaving as a column. So, the compression strength, compressive strength FCD, that is the term used in IS 800, into this web buckling area, let it be web buckling AWB, depending upon the slenderness ratio lambda. From table 9C of IS 800, we can calculate the value of FCD. Then multiply it with this web buckling area, we will get the web buckling loop. That strength should be greater than the external concentrated load or support reaction. Now, how we will calculate this one? I will explain. Let us take this support reaction condition. If there is a bearing plate having a particular width B and the flange is placed, the bottom flange is placed over this, and there is a web and top flange. Support reaction is acting at this point. Now, this load is dispersed like this. This dispersion angle is usually taken as 45 degrees. Then, the buckling phenomenon is maximum at the center. So, when we reach this at the center point, what is the width of this section? If we know the depth of this section and the width of this bearing plate, we can easily calculate this width because the angle is taken as 45 degree. Okay, so it is very easy. This depth is h by 2, where h is the overall depth of the beam. So, once we know the bearing plate dimension, we can easily calculate this bearing width. Then, let it be a capital B. Then, that capital B into thickness of web, which gives this AWB. So, you can easily find what is the buckling stress. Here in one of the question paper, they asked what is the dispersion angle. It is 45. As per IS 800, it is 45. This question was asked in one of the GATE question paper itself. I don't know, I don't remember the year, but that question was there. See how simple it is. This is about web buckling. Now, web crippling. It is somewhat similar to web buckling. The only difference is that web crippling is a local phenomena, we can say. Local phenomena. Here also the web buckles, but the buckling occurs at this junction. Buckling occurs at this point only. A total buckling of the web is not occurring in this case. Here, as we saw in the previous case, there is a bearing plate having some dimension. Then the load is getting dispersed. Now, in this case, this ratio is taken as 1:2.5. As we discussed in the previous case, calculate what is the width. This width. Let it be B1. Then that bearing area or crippling area is crippling. That's why I am writing it as C. is B1 into TW. Then the crippling capacity, let it be FWC, is equal to FYW into B1 into TW. Now, how we will calculate B1? B1 is this width and bearing plate width is, let it be B. This dispersion angle is 1:2.5. Now, what is this depth? This depth is TF plus R, where R is the radius of roof and TF is the thickness of flange. If this crippling stress, crippling load carrying capacity FWC is greater than the support reaction or concentrated load, then that beam is safe. These are the five design considerations or failure modes of beams, steel beams. Actually, these are very simple topics. You can easily remember. There is no need for by hearting those equations, because the logic behind writing this equation, I think it is clear to you. If you understand the logic, you can easily remember these equations. You can expect one or two simple questions as I explained earlier from this portion. So let us hope some simple questions from this. I think it is clear to all of you. Thank you.